5.8 billion light years away from Earth, there is something so colossal that astronomers are still arguing about what it really is. Some say it has 40 billion times the mass of our Sun, others say 100 billion. And the difference between these two numbers isn't just a technical detail. It's the difference between the largest object humanity has ever detected and the largest object the universe itself allows to exist. This object has a name, Phoenix a star, and the man who found it almost couldn't believe it was real. August 15, 2012. A young Hubble Fellowship researcher at MIT sits in a NASA press room. His name is Michael McDonald. For 30 years, astronomers had been searching for something they had almost given up on finding: a galaxy cluster where stars were being born as fast as the universe could make them. McDonald found that there, new stars are forming at a rate of 740 per year. For comparison, the entire Milky Way produces just one. This is the Phoenix cluster, 1,000 galaxies, 2.5 quadrillion solar masses held together by gravity. And at its center, hidden inside the most violent star factory ever observed, is the solitary object. It's the most massive solitary object ever recorded by humans. It's important to briefly explain what a Hubble Fellowship is, as it matters for the rest of the story. It's the most competitive position a newly graduated astronomer can get in the United States, created precisely to fund those who are about to change something in the field. McDonald had just won this fellowship when he came across the object that would define the rest of his career. To understand what McDonald found, we need to go back to 1957 to Mexico, to an observatory called Tonantzintla, where a small telescope photographs the constellation Canes Venatici. On one of the photographic plates, a faint blue dot appears. The astronomers catalog that as object number 618. Do they think it's a star? They're wrong. The light they photographed had left its source 10.4 billion years ago, long before Earth even existed, long before the solar system existed, almost as long as the age of the universe itself. It's not a star. It's a quasar, a black hole surrounded by superheated gas, spinning inward at thousands of kilometers per second, screaming energy as it dies. This is TOM 618. A quasar, if you've never heard the term, is basically a black hole feeding so fast that the very disk of gas around it starts to shine brighter than an entire galaxy. It's not the black hole that you see. Black holes don't emit any light at all. It's the material being torn apart before it falls in. TOM 618 was only recognized as a quasar in 1970. 13 years after it had been cataloged as just an ordinary star, when a radio survey in Italy picked up emissions that a normal star would never produce. It's worth noting that there are only two real photographs of black holes in the history of astronomy. Neither of them is of TOM 618 nor of Phoenix a star, because both are too far away and too small in the sky for any current instrument to resolve. The first image came in 2019 of the black hole at the center of the M87 galaxy, taken by the Event Collaboration Horizon Telescope, a network of radio telescopes spread across different continents, working in sync as if they were a single telescope the size of the Earth. The second came in 2022, showing Sagittarius, a star, the black hole of our own galaxy. Everything we know about TOM 618 and about Phoenix a star comes from other methods. No camera has ever directly captured their shadow. The astronomers who cataloged the object in 1957 were called Braulio Iriarte and Henrique Chavira. In the original note, they described that point of light as decidedly violet, a way of saying this doesn't look like an ordinary star, but we don't know what it is. It took over a decade for anyone to discover what it truly was. For decades, this object held a unique title: the largest black hole humanity has ever found. The exact number depends on which method you use to measure. In 2004, the astronomer Oded Shemesh and his team measured the width of a specific hydrogen spectral line, called the H-beta line, in the gas swirling around the black hole. The wider this line is, the faster the gas is spinning. and more mass needs to be there to keep this gas in orbit. The result was 66 billion solar masses, the number that circulated for 15 years as a reference. In 2019, a new analysis conducted by Jongo Guji and colleagues using more refined models of how this gas is actually distributed around the black hole revised the number down, 40.7 billion. The same technique, applied more carefully, delivered a result 40% lower. It's the same kind of revision that would happen years later with Phoenix, a star, only on a smaller scale. The event horizon of TOM 618, even using the revised number, extends about 1,300 times the distance between the Earth and the Sun. If you place TOM 618 at the center of the solar system, its mouth would swallow the orbit of Pluto dozens of times over. For half a century, this was the undisputed king. The only black hole that science treated as practically confirmed in this monstrous mass range. And then Michael McDonald looked at Phoenix. 2010 Antarctica. A 10-meter diameter telescope stands still, frozen at the South Pole. It's not looking for stars, it's not looking for galaxies, it's looking for shadows. When the oldest light in the universe, the radiation left over from the Big Bang, the so-called cosmic microwave background, passes through a very massive galaxy cluster, this cluster leaves a mark on that light, a subtle bruise, called the Sunyaev-Zeldovich effect. The South Pole Survey catalogs hundreds of these shadows scattered across the southern sky. One of them is different from anything astronomers had ever seen. It is buried in the constellation Phoenix, about 5.8 billion light-years away. In 2012, Michael McDonald pointed NASA's Chandra X-ray Observatory at this shadow, and what he sees breaks a rule that had lasted for 30 years. In every galaxy cluster ever studied, the central galaxy was dead, cold, quiet, with no new stars being born. The theory said that this was impossible to get around. The supermassive black hole at the center always won this battle. It heated the gas around it, pushed that gas out with jets of energy, and prevented any new stars from forming there. That's how it was the whole time astronomers observed this type of system. This stalemate even has a name in the literature: the cooling flow problem. According to calculations, the gas at the center of the cluster should cool fast enough to form hundreds of solar masses and new stars every year. But when astronomers pointed their telescopes at these centers, they almost always found a red, spherical, and completely inert galaxy, because the central black hole itself was reheating this gas before it could condense into stars. The previous record for star formation in this type of environment belonged to a cluster called Abell 1835, with about 100 new stars per year. Phoenix came in doing almost 5 times more than that, and still competing in total mass with another giant informally named El Gordo, which until then was the largest known cluster. McDonald, in an interview with MIT News a few years later, compared a galaxy cluster to a cup of coffee. A cup of coffee at 10 million degrees? He said that even a cup of coffee at 10 million degrees will cool down if you don't keep reheating it all the time. The Phoenix cluster was the first cup that someone picked up at the exact moment it was really cooling down. That's why 740 stars are born there every year. That's why the central galaxy is alive instead of dead. And that's why the black hole at its center became the center of a debate that continues to this day: Phoenix A star. The most famous estimate of its size comes from a theoretical paper from 2016 based not on speculation, but on the size of the galaxy that hosts this black hole. A statistical extrapolation like, galaxies of this size usually have black holes of this size. The number that came out of that was 100 billion solar masses. That's the number that spread across the internet. It's the number behind practically every viral video about the subject on YouTube. If it were correct, the event horizon of Phoenix A star would stretch for 4,000 astronomical units, multiple times the distance between our Sun and Pluto. It would swallow the entire solar system several times over. It would be more than twice the size of TOM 618. It would, without question, be the largest object in the known universe. But here's what almost nobody mentions when they repeat that number. In 2019, McDonald himself, the man who first discovered Phoenix, came back with better data. Direct measurements using Chandra, Hubble, and the Very Large Array Radio Telescope Array in New Mexico, as well as other radio telescopes. The improvement in data quality, as he himself described later, was 10 times greater compared to previous observations. And the number he published wasn't 100 billion, it was 5.8 billion solar masses. To give you an idea of proportion, ton 618, the former king, is between 40 and 66 billion. If McDonald is right, Phoenix A isn't the biggest. It's something close to 5 to 10 times less than the number that went viral. So which one is correct? Here's the honest answer. To truly measure a black hole's mass accurately, you need to see stars orbiting it. You need to track their movement year after year and calculate the mass from their orbital speed. It's the same physics that Kepler used to describe the planets, only applied to an object that doesn't emit any light. That's how the black hole at the center of our own Milky Way was measured. It was Sagittarius A star. 4 billion solar masses, confirmed with such high precision, confirmed that it earned the 2020 Nobel Prize in Physics for Reinhard Genzel and Andrea Ghez. Their team spent almost 3 decades tracking a specific star, named S2, which completes a full orbit around Sagittarius A star every 16 years, getting close enough to the black hole to feel the effects of general relativity on its own motion. But Phoenix A star is farther away, 5.8 billion light-years. You can't see the individual stars orbiting there. You can't track their movement. What we have is an educated guess, based on indirect signatures. McDonald's estimate, 5.8 billion, comes from the X-ray brightness of the gas around the black hole. It's a measurement of the energy that this gas emits as it's pulled in. The famous number 100 billion comes from the size of the host galaxy, extrapolated by a statistical relationship that works well for ordinary black holes, but that no one has tested in something as extreme as Phoenix A star. Both are well-founded estimates. Both could be wrong. Phoenix A star is sitting somewhere between 5.8 billion and 100 billion solar masses, and the universe for now isn't revealing which one is real. There's an idea that runs through much of the history of physics and works well for this specific moment. Serious science isn't about being certain. It's about knowing honestly the exact size of your own doubt. It was more or less this spirit that led McDonald's to publish a number 10 times smaller than the one that had gone viral, even knowing that the larger number would keep being repeated for years. Why is this disagreement so important? Because it runs into a much deeper question. Is there a maximum size that a black hole can reach? There's a well-established relationship in astrophysics called the M-sigma relation. The greater the velocity dispersion of the stars in the central bulge of a galaxy, basically the faster these stars move in random directions, the larger the black hole hidden there tends to be. It's this kind of statistical relationship that produced the number of 100 billion for Phoenix A by extrapolating the size of the host galaxy. The problem is that no one has tested this relationship in a galaxy as extreme as this one, because there simply isn't another like it to compare. In 2009, astronomer Priyanvada Natarajan from Yale and astronomer Ezekiel Trister proposed a self-regulation mechanism. As the black hole grows, the very gas disk that feeds it starts to radiate so much energy. Near the theoretical limit, known as the Eddington limit, the point at which the pressure of emitted light starts to push the gas away with more force than gravity can pull it back, it pushes the remaining gas away, literally clearing out the region around it. According to the original calculation by the duo, this should cap the growth at around 10 billion solar masses. Years later, in 2016, the British astrophysicist Andrew King refined this calculation, taking into account the instability of the accretion disk at extreme masses, reaching a ceiling of approximately 50 billion solar masses in most cases, but pointing out that in extreme conditions, with the black hole spinning at the maximum possible limit and in the same direction as the disk that feeds it, this ceiling could rise to as much as 270 billion solar masses. After that point, according to his model, The accretion disk itself becomes too unstable to sustain quasar luminosity. The black hole simply stops growing that way. Not because there's a lack of gas in the universe, but because the very light it produces drives away its fuel before it can swallow more. If Phoenix A really has 100 billion solar masses, it would be very close to the ceiling, calculated by King for a regular black hole, not spinning at the extreme limit, but still near the edge of what physics seems to allow. While this discussion about Phoenix A remained open, another discovery reignited the debate about this theoretical ceiling. And this one, it's worth noting, came from Brazil. In August 2025, a team led by Carlos Melo Carneiro from the Federal University of Rio Grande do Sul published in the monthly notices of the Royal Astronomical Society the detection of a black hole with 36 billion solar masses at the center of the galaxy that forms the cosmic horseshoe, a gravitational lens system about 5 billion light-years away. The technique used had nothing to do with gas brightness or spectral line width. The researchers combined the gravitational lensing effect, the way the mass of the galaxy distorts and bends the light from a much more distant galaxy behind it, creating an almost perfect ring in the sky with the movement of the stars themselves around the galactic center. It's a third method completely independent from the two used in Phoenix, and it found a dormant black hole with no active quasar just by the deformation its gravity causes in the space around it. The result came dangerously close to the ceiling, calculated by King for the most common cases. But it's a piece of the puzzle showing that the largest objects in the universe really do seem to run up against a real physical limit. There is even a theoretical class of hypothetical objects that are even bigger, named, without much ceremony or seriousness, stupendously large black holes. The idea was formalized in a 2020 paper by physicists Bernard Carr, Florian Kuhnel, and Luca Vicinelli, is that these objects wouldn't grow slowly, swallowing gas and stars over billions of years, but would have formed almost instantly in the primordial universe, as colossal primordial black holes. No one has ever confirmed their existence. None of the black holes we know today come close to that scale. But the simple fact that physicists need to invent a category for objects even larger than the limits already calculated says something about how little we understand the upper limits of the physics involved. The James Webb Space Telescope points its mirrors at the Phoenix cluster, more than a decade after McDonald first looked at it. The results are published in the journal Nature in February 2025, signed by a team led by MIT graduate researcher Michael Reif. Using Webb's mid-infrared spectrometer, an instrument sensitive enough to separate wavelengths that any previous telescope saw as a single blur, the team finds, for the first time in any galaxy cluster, gas at an intermediate temperature, about 300,000 degrees Celsius, exactly between the extremely hot gas surrounding the cluster and the already cold gas. Where do new stars come from? Reif described the signal from this gas, detected by ionized neon atoms, as something that practically jumped out of the data as soon as the team looked at the spectrum. McDonald compared the process to a ski resort. The Phoenix cluster has the largest reservoir of hot and cooling gas of any cluster ever observed. Like it's the busiest ski lift on the mountain, taking more skiers to the top than any other. But until then, no one knew how many of those skiers actually made it to the bottom. If the math at the top of the mountain didn't match the math at the base, something was missing along the way. Webb finally found the skiers halfway down the course. The intermediate gas was exactly where the theory had predicted it would be for decades, but no previous instrument was sensitive enough to detect it. That means something uncomfortable. Finally, Phoenix A keeps feeding. It keeps growing. Slowly, almost imperceptibly on a human timescale, but inevitably on a cosmic timescale. I need to admit something here. Before I delved into this specific cluster, I also had a round number stuck in my head. 100 billion, the largest object in the universe, period. It's an easier number to repeat, easier to put in a catchy title. I found out that the very scientist responsible for the discovery preferred to publish a number 10 times smaller, knowing that this would go against what had already gone viral. That slightly changed the way I read any headline about the largest object ever found. Not because the big number is a lie, it's still a real possibility supported by a legitimate method. But because scientific honesty, in this case, means publicly admitting that you don't know, even if the public prefers a definitive answer. When McDonald spoke about the subject again to MIT News, he described the Phoenix cluster as the only specimen of its kind ever discovered, a natural laboratory to study a kind of physics that, according to the prevailing theory until then, shouldn't exist. If Tom 618 is the runner-up, with something between 40 and 66 billion suns, then Phoenix A is the champion in contention. Sitting somewhere between 6 and 100 billion, then maybe this is the strangest era in recent cosmic history. The era in which the largest objects the universe will ever build are devouring their very last meal.